thanks to the organizers for putting this together and all the great discussion that's been going on. I'm going to be talking a little bit more about the volcanic problem, or the explosive volcanic problem that George started us off talking about a little bit this morning. So I won't talk so much about the magmatic system, but things that are ejected into the atmosphere explosively. And because their names got partially cut off, I just want to acknowledge the contributions of various postdocs and students that have worked in the group on things I'll be talking about today, and I'll bring up their contributions as we go. But we have Josh Mendez, Mary Benage, and Eric Brereton, and Alison Kubo. I'm going to spend just a couple minutes orienting ourselves with the volcanic problem. And so an explosive volcanic eruption ejects quite a bit of volcanic ash, volcanic gases, and some other larger class into the atmosphere. And when you're thinking about volcanic ash, this is it's composed of fragmented melt, so glass essentially, and crystal fragments. So very bad to breathe, very bad for jet engines. And a lot of people kind of relate to this one example of May 18th, 1980 eruption of Mount St. Helens that dispersed ash quite widely across kind of northern US. Of course, there are lots of other sorts of eruptions. I like to point out this nice eruption from 1932 in Quizapu. It's in Chile. And what looks like snow here in the looking from the vent all the way into Chile is actually pumice from this 1932 eruption. So you can see it covers a really large area. You also see a few different sorts of deposits when you look at detail. You see sort of mantling deposits that come from material that's been injected into the atmosphere and fallen from plumes. But you also see laterally heterogeneous deposits too that are associated with gravity currents. And I'm going to talk a little bit about both today. And of course, like many of the problems we've been discussing, this is also a multi-scale problem, which presents a lot of the issues we have to deal with, where you have volcanic ash, some of which is tens to hundreds of microns in size. That determines a lot of the important physics of what's going on, but of course we have to worry about ash that's being distributed over hundreds of kilometers or larger. So today, the questions I want to touch upon, and I'll probably have more questions than conclusions, frankly, is how does preferential concentration of material impact flow dynamics and some of the hazards from volcanic flows? How can we understand dynamics in these opaque systems? They're hard to see through and they're dangerous and hard to predict. How can we get information from them? And it's a big open question. And then how does microphysics play a role? And I'll particularly talk about how does material damage and comminution, how things break. How does that determine some of the dynamics of these flows? So this figure, the May 18th, 1980 eruption, illustrates a lot of the important multi-phase dynamics that go on. I won't talk about all these, but just to get more into one of the things that's important in volcanic eruptions, you have this melt in the system that George is talking about. Imagine it being uncorked. A lot of the dissolved volatiles, which are primarily water, carbon dioxide, sulfur dioxide to a certain extent, will start to dissolve into bubbles. That will accelerate, it'll fragment, and then you have this mixture of gas and particles that will accelerate often up to, we think, the speed of sound, so a choked condition at the vent, and then form either a buoyant column, sometimes we call it a Plinian column, or a gravity current if it's denser than the atmosphere. Sometimes I'll say pyroclastic density current or gravity current in this talk. So these are all kind of important processes that can occur. You can have entrainment near the vent that might be modulated by shocks, and obviously the turbulent flow above the vent. Sorting and sedimentation of particles from the plume is, of course, very important. All sorts of microphysical effects, all the sort of cloud physics that we were talking about earlier in the week. Some variation of that's going on here too. Compressible effects in terms of shocks, and of course that choke condition. And then of course entrainment into the pyroclastic density current, which I'll talk a bit about today. And then potentially bad interactions like erosion. So I want to start off by talking about the conduit system, kind of move into talking about the shocks right above the conduit, and then move towards the end of the talk to talk about pyroclastic density currents, which I think we'll hear more about after this talk as well. But just to orient you, if you haven't been thinking a lot about compressible flows, this is sort of just a simple thought experiment using kind of a very sort of first order approach of conservation relations of mass and momentum. But if you rearrange these expressions for compressible flow, you can write this expression here that tells us how the change of velocity is compared to a change in cross-sectional area that's modulated by this Mach number, which is m here. It's a ratio of your velocity of your flow to sound speed. And you see that if Mach number is less than 1, then we kind of get the usual association of change in area is positive, change of velocity is negative. So as things get wider, you slow down. The opposite, of course, occurs if Mach number is bigger than 1, and so this gives rise to this idea of a choked condition. We have a constriction at the top of the system where you reach the sound speed, and then above the vent you go speeds greater than the speed of sound, so Mach number bigger than 1. And so the classic approach in volcanology is to treat this as a boundary condition at the top of the conduit system, and oftentimes we'll use kind of a mixture sound speed to calculate that velocity. So as you put in more particles, you reduce the sound speed. This assumes, of course, that the particles are really well coupled with fluid, and it's a really open question about what happens when they're not. So we've conducted a number of simulations to try to get at that question, and to try to get at some of the heterogeneity that occurs in the conduit system. So if you're picturing this conduit system, you can picture it like we all do, which is sort of like a pipe. It's almost certainly not a pipe, but it's sort of our approximation of this conduit system. And in this particular set of simulations, this is a multi-phase set of simulations, a multi-continuum, and I'll get into a bit more detail about this later. But in this set of simulations, we have a larger fraction. These are pumice, 10 to the -1 meter pumice, and it also includes a volcanic ash grain size. We also conducted a number of experiments to see how particles break up. So higher energy collisions break up particles more. And we put that in as a subgrid parameterization in these models. And what you see, first of all, is that the larger Stokes number pumice particles form these nice sort of clusters. These are primarily happening due to particle collisions. So it's not necessarily being shaped by the turbulence in the flow here as more modulated by collisions. The idea is you have more collisions that are slowing down. It's a positive feedback. And that, in the end, creates particles that are more concentrated in regions coming out of the vent and a little bit more dilute coming out of the vent. And so you get this sort of pulsing at the vent with these bigger particles. And that's illustrated here. This is time, and this is volume fraction. Because we have breakage or comminution in this simulation, you also, as you get further and further from that initial fragmentation front, you get more and more fines. And this also changes the dynamics and the flux coming out of the vent. As we exit the vent, then we enter a region where we often think there'll be some sort of shock situation. Now, classically, in the field of volcanology, we've looked at pressure balance jets, so that pressure of the vent is equal to the atmospheric pressure. But there's good reason to think that in many cases this is not the case, that we have pressures exceeding the atmospheric pressure, and so we expect some sort of shocks. This is from some really nice work of Darcy Ogden, looking at the implications of this. She went on to estimate some overpressures of some systems like Mount St. Helens, which she estimated was significantly overpressure at the vent. The hard part is, while this may have important implications for entrainment and other parts of the physics of the system, it's really hard to see. We can't see into these systems very well. So some of what's driving what we're doing is thinking about how can we get information about this when we can't see into the vent. And so this kind of pushed us into a sort of field that we never expected, but it's turned out to be very interesting. It's interesting in its own right, but also interesting for what it tells us about the bigger system. And this has to do with looking at charge on particles and how this can relate to discharge. So oftentimes you see these pictures of volcanic plumes and you see this beautiful lightning, and it's very dramatic. And the reason, well, one of the reasons this occurs is that you're charging the particles. And there are a few different mechanisms, and I'll get into these in a bit. But the idea is that we can create, differential charge on different size particles and different types of particles. Separating these particles creates a potential field that can then relate in discharge. And the nice thing about this is that, of course, we can see the lightning, but it's also producing all sorts of other electromagnetic radiation, including radio waves, which are easy to detect at great distances. So to kind of close the system, we've been looking at various processes that could create this electrical charge. And I don't know if that's going to play or not. But the idea here is that we can create charge by breaking material. And our model for this system is Prince Rupert drops. And if you've ever encountered these are amazing. You sort of take molten glass, you drop it into a bit of cool liquid. It will form these sort of tadpole-shaped objects. And I wish the movie was playing, but if I snap the tail, you get a fragmentation wave, and that thing would fragment to lots of little shards. And it's great because it's a way for us to create fragmentation without actually physically hitting the system. We can measure charge on particles in that system. We can look at tribocharging. This is when particles are colliding with each other and charging that way. This typically results in negative charged small particles if we have a system where you have big and large particles. And then we've also looked a little bit at modulation of charge just due to atmospheric interaction. And of course, this is in many ways a really dirty thunderstorm, a really energetic dirty thunderstorm, in that we have volcanic ash that's rising really quick. What's driving all this mostly is water vapor. So that's the biggest component of dissolved gas in volcano. And so all these mechanisms can create charge. We've kind of favored looking at a lot of the tribocharging mechanism recently because we've been looking at signals that are just coming out of the vent when we don't expect a lot of water to have condensed onto our grains yet. Well, one of the really interesting things that came from this was work conducted by Josh Mendez, is that we can take a picture we had before of that barrel shock system, and we can take a particles perspective through that system. And in this case, I'll just direct you to this plot up here. Let's follow the red curve. So if we're at the vent and we're accelerating, going to supersonic velocities, we're actually reducing our pressure to considerably less than atmospheric pressure until we get to the shock system. And here the K's are the overpressure ratio. So here would be 10 times atmospheric pressure. So we have this pressure signal, and if we then look at this in terms of the maximum charge density allowed before discharge, this is a curve sometimes referred to as a Paschen's curve. We can follow this line here, and what we do is as we decompress, we will hit this curve and we will start having discharge up until we get back to the shock, and then we should basically be shutting off the system. It's just easier to discharge when we have less atmospheric pressure. There are other things that might modulate this, and we're looking into this right now in terms of adding particles into the system. Could change how discharge is occurring. The nice thing about this is it allows us to look at how discharge is connected to pressure in a way that we couldn't perceive very well before. And this is from a set of experiments that were conducted in Germany. This is looking at a shock tube. So the shock tubes would be below here. So you have pressurized gas and particles that are entering to atmospheric pressure, and they're creating these discharge events. And then we can record all these discharge events, and maybe hard to see here, but these are different empirical relationships for how height should vary, of the shock should vary versus overpressure ratios. And you can see the discharges, by and large, are kind of falling in that realm. So we can actually map out where discharges are occurring, and that tells us something about the overpressure of the event, something we would have a really hard time getting at otherwise. So I just wanted to illustrate that as one mechanism where not only does the sort of subgrid or closures, condition provide interesting dynamic physics, but also tells us some information that we can gather from the field. Now, the second half of this talk, what I want to do is focus mostly on gravity currents or pyroclastic density currents. And I'm going to primarily use computational tools and some field observations to look at some of the dynamics of these currents. And this follows along with some of the stuff that Garrett presented earlier. And of course, the motivation here is that pyroclastic density currents are really fast moving. They concentrate all their energy near where populations live and buildings. And so this is pictures kind of before and after the eruption of Mount Pelée in Martinique, where this town was basically destroyed by this event. And I'm going to use, again, multi-continuum approaches to illustrate some different dynamics here. Here I'm just showing a scaled version of these equations. The idea here is it illustrates a lot of the dimensionless numbers that George had brought up before. And here I've just kind of brought them down to, what part of the problem in terms of where I listed those critical features around that volcano earlier, how they map into it. So of course you've got, in this case, a Mach number, Reynolds number, and Stokes-Froude number for steady and unsteady forcing. So the idea with these, like some of the multi-continuum approaches we've seen before, the idea here is in this context, we're going to treat the gas as a continuum, of course, but also different particle classes as a continuum. So it will have, multiple particle phases. And when I say phase, in this case, each phase will be represented by this set of equations. They'll have the same density and size. And we can look at how there's exchange between those phases if we'd like, if we have a good closure scheme. That's kind of how we'll use it. And where that fits typically when we're looking at a lot of these closure schemes, it will be in these kind of source terms. And you can think about this as, production of fines, for example, earlier, that's how we would parameterize it. We would take mass from a bigger phase and dump it into a smaller phase, for example. The kind of conceptual picture I want you to start thinking about, although there are, lots of little issues with this too, but is illustrated here. And so the idea is, pyroclastic density current term refers to a lot of different physical phenomena. They're all gravity currents, but they can have various concentrations of particles. They can be extremely dilute and turbulent, or they can be very concentrated and driven by pore pressure effects. And so you get a lot of different dynamic interaction as a result. And so, and one of the things we've really focused on is how does this particle concentration gradient influence dynamics, things like entrainment. And so to do this, what we've been involved in is a collaboration with a number of folks thinking about benchmarking using the experiments that Garrett had presented. I think he may show something about this, or something about these experiments again after this talk as well. The idea, these are large-scale experiments being conducted at Massey University. The numerical part of it is kind of a truncated version. We're not simulating the big drop from the hopper onto the bed, but we're starting somewhere downstream from that. And this is just kind of a look at the flume. And our goal here, of course, was to compare numerical calculations to the experiments as a benchmarking exercise, but also to try to look at some of the physics. So I'll just show a simulation here looking at concentration fields. This is just volume fraction of all particles. This is a log scale, so the red is higher concentration. And we'll look at some more details of this a bit before, but one thing that we've really been interested in is in entrainment. And so for entrainment in these calculations, what we've done is we've assigned a surface or an isosurface to a particular volume fraction, and then looked at the flux of gas through that isosurface, and looked at how that develops. And if we do that, we look at averages in space and time, we get these sort of entrainment coefficients that are quite large. When you look at pretty dilute isosurfaces, and of course, if almost more of a mixing problem, frankly, as you get to higher concentrations, it's harder and harder to mix into this. We're having to work against gravity. Yeah. Yeah, so this is just sort of the classic definition of entrainment, where we have, in this case, we're normalizing it to this velocity. In this case, the U is basically the normal to any of these surfaces in our calculation. And in box models, you just do like you just whatever goes in there. Just to give you some sense of what's going on here, I've just put a layer of just passive tracers so we can see how the current's overriding it and mixing into the system. And we see that a lot of it, of course, is going up in the mixing into the top part of this current in Kelvin-Helmholtz instabilities, and a little bit in the kind of lobe and cleft instabilities at the front. So how does that, so what I want to take from this is though that we're having a hard time mixing into the current because of these particle concentration gradients. And so the bottom of these currents tend to stay warm. The question is, does that bear out when we go to the field? And to do this, we'll go to Tungurahua. It's a volcano in Ecuador. It has these boiling over eruptions. It's a highly technical term, just kind of boils over. And this is kind of what you see from the observatory, very obscured. We have some seismic signals from this. The main point here is that these are broad seismic signals, broad frequency spectrum. If you look at the deposits themselves, if you look high in the volcano, you have nice big levees of these big clasts. And if you look further down the volcano, you have nice big dune features where the flow is mostly avulsed from its channel. Right. And we see this in the numerical results as well, where you have a strong concentration in the channels, and it's producing a lot of these, features that have more to do with particle-particle interaction, and then more deposits that are shaped by particle-fluid interaction when you go outside the flow. And this is shown very nicely by a set of numerical experiments that Alison Kubo has conducted. And I'll just direct you to that paper for that. I just want to say one last thing is that for these calculations, Mary Bandage also calculated some currents down from Tungurahua looking at not only the thermal field, but also embedding in this some Lagrangian tracers that included bubble growth. And so those big, we call them bombs in volcanology, the big class. They're actually big enough and warm enough that they're still exsolving gases as they're being transported and the bubbles are growing. And as a result, you can look at where those are quenched in those rines, thickness of those rines, to get a proxy for temperature. So kind of like a temperature Lagrangian tracer. And she did this, and when she did this, she found that most of these were really being transported in the lower part of the current and staying very warm, even though the outside of the current was not so warm at all. So you really have this kind of, it's a simplified view, but a transition between those two. So I'll just sum this up by looking at some of these entrainment, and this will be a point for discussion, perhaps. And that is that we measure from the paleo simulations entrainment up here. This compares to some other sort of classic experiments that have entrainment down here. And this other curve here was suggested by these authors to be indicative of higher Reynolds numbers. I don't know if that's the case, or we're just measuring different things, but certainly something we have to sort out if we were to use these experiments as proxies for simplified models, like box models or 1D depth average models. So I'll stop there.
Questions for Joe?
How important is the Earth rotation?
What's that?
I mean, the Earth rotation for these gigantic structures.
Oh, yes. Yeah.
Coriolis effects must be quite important, right?
Yes, if you're looking at the large-scale plume, yeah, that would become very important. Especially, like I showed some pictures of the Iceland eruption.
But in these simulations, there's no Coriolis.
The PDC simulations, no, yeah, those are kilometers or two usually. Yeah.
You mentioned that the velocity, the speed of sound is reduced because of the particle loading.
Yeah.
So at the exit, can you give us an idea of what is the volume fraction of solid material and how big is the speed of sound approximately?
It can vary quite widely depending on where you have a buoyant column. It's always denser, almost always denser than the atmosphere. A few % of particles is not uncommon. But it usually is denser than the atmosphere. And so to get the big buoyant plumes, you actually are relying upon entrainment.
Yes.
And velocities are order 100 meters a second.
Okay, yeah. Thanks.
Yeah.
Right. Yeah, I think in the first part of your talk, you mentioned a positive feedback involving collisions.
Yes.
But
yeah.
I didn't really understand. Could you explain it again? I don't know if you.
Yeah, I really didn't get into this, but the idea is that it's sort of, you have particles colliding with each other. These are inertial particles, big particles. And as they do, they're moving a little bit slower. And so that they basically sort of pile up. It's sort of like the freeway argument where you have, a bunch of cars and you have a bunch of traffic in front of you, and you kind of catch up to them and you're stuck from going around them. Yeah. Yeah. It's maybe shaped a little bit by fluids, but these are very large Stokes number particles. Yeah.
And the restitution coefficient is
0.5-ish.
Yeah, quite small compared to glass beads, for example. Other questions for Joe?
Thank you for great talk. Is there some scaling to explain maybe entrainment is scaled with Richardson number, but there should be some prefactors?
Yeah. Well, the idea here is that as you're having to do more work against gravity to mix, right? You have to have more shear to mix when you have a larger density gradient. And that's kind of the idea here. The mismatch here, yeah, that's something that I think it's either, I suspect it's actually mostly to do with how we're measuring it rather than anything inherent. So.
other questions.
Could you explain the undischarged place a little bit more? I couldn't catch up very well on some Germany experiments, so relating to your work.
Of electrical discharge experiments?
Yeah.
Yeah, so these are experiments. So there's several experiments. I'll talk about the tribocharging experiments. The idea there is you create a fluidized bed. And the idea there is just to create lots of collisions between grains. And we measure the charge on the particles in a few different ways. We either have just a big hoop and we measure current, or we actually will take some of the particles and actually measure them through a Faraday cup and get the current from that and look at the charge. The discharge in the shock tube is basically not as controlled. Particles and then it goes into a, through a shock structure.
What happens to particles when they go through that shock front? The shock front must be extremely thin.
That's
So
right.
10 to the
it's
minus 8 meters.
That's right, yeah.
So
There's a suggestion, there's some recent numerical simulations conducted by some collaborators at the Department of Energy that suggest that this sort of smears out the shock, that you get less, abrupt shock interface due to the particles. I don't know if we've been able to really confirm that with experiments yet. So.
And how about the lateral shocks you showed, the barrel shocks? Do you see those in this?
You do kind of, you do kind of in the, you can see the discharge kind of outlining them as well. Yeah. In the field, yeah, because we don't really have a great view of this. This would all be interior to like that big column that we saw from Mount St. Helens.
Any last questions? Otherwise, we'll have Gert come up and get himself set up. Thank you, Joe.